This is part 1. As you'll see, compilation involves a wide range of themes in the field of computer science. Indeed, the scope of this topic is so diverse. Part 1 of this series is an overview of the stages of compilation. Compilation means taking source code written by a programmer in some high-level programming language and turning it into object code, that is, executable machine code that a computer can understand. Compilation is done by a software utility known as a compiler. There's no one way to compile source code. New programming languages and their compilers are often developed hand in hand, so the inner workings of a compiler depend very much on the language of the source code being compiled. And because a program is compiled to be run by a particular type of processor, exactly how the compiler is implemented depends on the architecture of the target machine. So what makes a good compiler? For a start, it must work correctly with any program written in the high-level programming language that it was designed to compile. It must detect all static errors. This means it should identify all of the errors that break the rules of the programming language. A compiler can't, however, be expected to catch dynamic errors, those which are detectable only at runtime and might cause the program to crash if they're not trapped. Nor will a compiler discover logical errors, those which by definition don't crash the program but might cause it to produce the wrong output. A compiler should produce clear and meaningful diagnostics. If errors are found when a program is being compiled, the error messages should be unambiguous and ideally pinpointed within the source code. A good compiler won't stop processing as soon as it hits one error. In a single attempt to compile some source code, the compiler should find and report as many errors as possible. A good compiler generates optimal machine code. However, optimal implies perfect, and it's unlikely that any compiler can ever generate perfect machine code. A good compiler will nevertheless attempt to optimize the machine code that it outputs. It will look for ways to replace statements and constructs with alternatives that can be executed more efficiently. Compilation should be quick. An agile programmer will no doubt want to compile and test their source code lots of times during development, without having to wait around each time another change is made. A compiler should be easy to use. Many compilers can be launched from a command line and include a large range of options to control the amount of debugging information generated along with the object code. Others involve a simple menu option built into an integrated development environment. A compiler might even launch automatically when an attempt is made to run some new code from within the IDE. There's much wisdom in building a modular compiler, with as little coupling as possible between its various components. This approach allows parts of a compiler to be reused with a variety of source code programming languages and a variety of target machine architectures. Finally, like all good software, a compiler should be well documented and, if necessary, easy to maintain. There are three main stages when it comes to compiling a program. Lexical analysis, which is rather like taking a sentence written in plain English and breaking it up into separate words and punctuation symbols. Syntax analysis, which is like checking that a sentence actually has meaning. And machine code generation, which is like translating a sentence into another language. A compiler generates the ones and zeros that can be understood by a processor, but it may well edit this machine code for speed and space efficiency at the same time. So code generation and optimization are often thought of as one stage. Notionally, one stage of compilation is followed by the next, but in reality, as you'll soon see, this is not necessarily the case. For example, lexical analysis and syntax analysis occur together. Lexical and syntax analysis depend on the high-level programming language being compiled, but are independent of the architecture of the target machine. Lexical and syntax analysis are therefore known as the front-end operations of the compiler. Code generation and optimization, on the other hand, involve generating machine code using only the instruction set of the target machine. This phase of compilation is known as the back end. Lexical analysis is performed by a component of the compiler known as the lexical analyzer. This is also sometimes referred to as the lexer or as the scanner. Syntax analysis is performed by the syntax analyzer. This is often referred to as the parser. The input of the lexical analyzer is the source code of a program as a stream of text. The output of the lexical analyzer is a stream of tokens representing the individual words of the source program, and these are fed into the syntax analyzer one by one as and when requested. The syntax analyzer builds an intermediate representation of the source program known as an abstract syntax tree. An abstract syntax tree is a dynamic data structure that represents the hierarchical nature of the source program. While it's being constructed, the compiler uses it to check that the rules of the programming language have been followed. The lexical analyzer might also create a symbol table, which is frequently accessed and modified during all stages of the compilation process. This contains information about the names a programmer has used within the source code, such as variable or function names. For some compilers, an abstract syntax tree is the only intermediate representation of the source code. The abstract syntax tree is the output of the syntax analyzer and the ultimate output of the compiler's front end. The abstract syntax tree is then converted directly into machine code. However, some compilers do more work in the front end. Before constructing the abstract syntax tree, a compiler might first build a less refined tree-like representation of the source program, known as a parse tree. Then it might combine information obtained by traversing the abstract syntax tree with information from the symbol table and generate another intermediate representation of the source code, a sequence of elementary program steps that look like assembly code. 3 address code is an example of an intermediate code representation. Some compilers create this low-level code after building the abstract syntax tree, while others will emit intermediate code at the same time as building the abstract syntax tree. In fact, some compilers go through the motions of building a tree with all of the syntax checking and semantic checking that it allows for, but only intermediate code is left behind. Low-level intermediate code provides opportunities for significant optimization. Optimization which is independent of the target machine architecture. Low-level intermediate code is easier to generate machine code from, and for some compilers this is the end of the process. But some compilers will even attempt to improve on this.